Okay, I'll be recording this presentation discussion. If the quality of the recording is good, I will upload it in Learn USL. Otherwise, I will put the presentation only, slideshow only, right? Okay, so today we are going to discuss on organic reaction mechanisms. That is unit 2 of your course material, right? Hope you all have gone through the book. Our day school CAT test is on January 1st, right? So maybe you all are aware of it, right? Okay, so I will start with the very basics and try to, as I always do, I have included some activities in the presentation in this day of the discussion. So you all have to have a paper and a pen with you to attempt those questions. So organic reactions, before we talk about the real organic reactions we are going to discuss today, let's see what a reaction is. Actually, what is happening in a reaction is we react some reactants, we call them reactants together to get products, right? So the process is called the reaction, right? So there are the two things what we react. Under reactants, we can talk about two things. That is the substrate. What is a substrate? That is the molecule or the molecules which undergoes a reaction. And there's another class which comes under these reactants, that is reagent, right? So reagent is the substance that is used to cause a chemical reaction. So without having a reagent, substrate won't react. Sometimes there are some substrate which undergo reactions on its own, but very rare. But usually we need to have the substrate and the reagent to for a reaction to take place. Right. So reactions can be divided into 4 main groups. In our study at this level, we are going to divide reactions into 4 categories like this. Those are substitution reactions, addition reactions, elimination reactions, and rearrangement reactions. Right. So under we put all the reactions what we study at this level under these 4 categories. Right. So substance which act as a reagent can be identified, categorized into several groups like this. They can be reagent, can be a nucleophile or an electrophile or a radical or a carbene, right? So by now you may know what these are, because at level 3 also we learned, we identify what a nucleophile is, what an electrophile is, what are radicals and what are carbenes. So I don't have to explain what they are now. Okay, so what will happen during a reaction? Now, during a reaction, a bond breaking and bond making take place. And in between, you can see reactive intermediates forming, right? So while these bonds are breaking and new bonds are forming, some intermediates can be formed, right? So the bond breaking can take place in several ways. We can group them as heterolytic cleavages, where carbocations and carbanions are formed. Or it can be homolytic cleavage. Cleavage means breaking of the bond. So it can, the bond can undergo heterolytic cleavage to give rise to carbocations or carbanions, or it can undergo homolytic cleavage. So by homolytic cleavage, you get radicals. And also pericyclic reactions can take place within the same molecules. Bond breaking and forming new bonds are formed inside the single molecule, inside the molecule itself, not without a participation of 2 different molecules. Right. So organic reactions are classified according to the change in the substrate. So you know what a substrate and a reactant is, right? So I have a exercise here. It is fill in the following table with correct terms, right? Now you can see there's a table. I have under the reaction, we have all these several types of reactions given here: nucleophilic substitution reaction, electrophilic substitution reaction, nucleophilic addition, electrophilic addition, and rearrangements reaction. So this name itself implies what is happening, right? So with that knowledge, you can fill the table, right? So try to complete the table. I have given one example. I have done one for you. I'm giving you 2 minutes. Even 2 minutes not necessary, 1 minute.
Madam, I can't see anything in the screen.
Can the others see the screen?
Yes, ma'am.
Yes, ma'am.
Then there it is a problem of your device. Try to log out and join again. And in the meantime, please put your name and registration number at the center, because I can get the auto-generated report also. But anyway, to be on safe side, if it is in the chat, it's easy for us to get the details. So good morning, madam. Can you upload 2021 online CAT papers? In 2021, we had this online MCQ papers. The paper was generated out of a question bank. So each individual got a different paper, because in the question bank, there were more than 400 questions. So I can't upload all the questions, and maybe next time also we will be using the same, because no individual was going to get the same paper, because the question paper was generated out of that 400 odd questions, and each one got a different paper. And even the answers were different. The answers were shuffling, questions were shuffling, and now question number 1, there were more than 15 questions. Okay, I think I have given enough time. It's very easy. This question is very easy. So you can see electrophilic is, again, substitution is there. The change undergone by the substrate is given in this reaction name. It is substitution. And the reagent is electrophile. And the third one, it's an addition reaction. And the reagent in that reaction is a nucleophile. And fourth one, again, addition and electrophilic addition. Rearrangement is the change undergone by the substrate is a rearrangement of atoms or groups. So there's no reagent, as I have mentioned earlier. Okay. So when you are writing organic reactions, reaction mechanisms, you indicate how the mechanism, how the reaction is taking place by putting arrows, and we call them arrow pushing mechanisms. So we have to use arrows correctly to depict the flow of electrons during the chemical reaction, right? So before writing the mechanism of a reaction, we should know the types of arrows we are going to use when we are writing mechanism. So you can see this first one is a regular arrow. It's a double-sided arrowhead is there. You can see it here. And it indicates movement of 2 electrons. And the next type of arrow, the second type of arrow we are using is fishhook arrow. It's a single-sided arrowhead, and it indicates the movement of 1 electron, right? So arrows are not used to indicate the movement of atoms. Remember that. So we are indicating by putting an arrow the movement of electrons, right? So movement of 2 electrons is given by this two-headed double-sided arrowhead, and movement of 1 electron is indicated by this half arrow, right? Or fishhook arrow. Right. So the second thing you have to remember is always start an arrow at an electron source or electron donor and end at an electron sink or electron acceptor. So it is clear here. Or electrons can move from a electron rich place only, and it moves to a electron deficient place, right? So electrons from electron source to a electron sink, right? Remember that. Otherwise, you will put the arrow from a place where there are no electrons that can be moved, right? It's wrong. And the third thing you have to remember is break bonds simultaneously to avoid overfilling valence or hypervalence orbitals, right? Now you know, look at these two examples. Now in the first one, what I have written is wrong because the valency of nitrogen is 3. But in this figure, in this structure, you have 5 bonds. So it's a hypervalent N atom, nitrogen atom. So this can never happen, right? So you can't put the arrow like this, right? It won't give a intermediate like this. So instead of this, you can write it in this way. The electrons move on to this nitrogen, and to have retain the valency of nitrogen, this bond has to open, right? So what you should write is this. So there are 4 bonds so that it has a positive charge here, and the bond is, since the bond is open, this is oxygen is going to have a negative charge, right? So always remember, don't have hypervalent atoms as the intermediate, right? And fourth thing you have to remember is break a bond so that a relatively stable ion or molecule is formed. So as shown here, bromine is the bromide, this group is a very good leaving group. When you break a bond, it will get removed as a bromide anion, right? So it's a stable anion, right? So it can take place very easily in a reaction when the anion or the cation formed is stable. Right. So I have given written some mechanisms here. Now, with the knowledge you have got, find out whether the mechanisms given below are correct or incorrect. All are incorrect. Actually, I have mentioned it here. All what I have shown here are incorrect. Correct them giving reasons. So try to identify what is wrong and find out how to correct them. Now with the knowledge, now I have been explaining you 4 things to remember when you are writing a mechanism. Find out what is wrong. And in the meantime, if there is a power cut, stay connected. I will try to restart the school. In case the power is gone, stay connected, please. Yes.
Can you move on to the very first 2 slides?
Then others are going to miss the slide. No. Okay. I'll give the others 5 minutes, not 5 minutes, 2 minutes to go through the 3 reactions, and then I'll go back to this one.
Okay, madam.
I will go back to this thing so that everybody can see the slides. Okay. This one. Or this.
No, madam.
This.
Let's start.
This one.
Yeah, yes, madam.
Okay. Okay, there's nothing. The 2 electron movement, 1 electron movement from electron.
Before that, madam. Before that. Yeah, that's. Before
Okay.
that, madam. Before that.
If this one, there was
Yes.
nothing. You don't have.
That's okay, madam. Enough,
Okay.
madam.
If you
Thank
think
you.
that you need you take a screen, the photo, right? Otherwise, going back is going to waste time. Right. Okay. Okay, let's see. Let's see. Now, the first reaction, what's wrong in it? Now, this bond opening is correct because the bromine is a good leaving group so that it can take 2 electrons and leave as a Br minus. But this is wrong. This is not an electron rich place, right? So from an electron deficient place, electron won't move. But the electron rich place is this one. There's a pi bond here. 2 bonds in the 2 electrons in this pi bond and 2 more in the sigma electron. So electron movement should start from the double bond, right? So see my explanation, backward arrow is this one. So it should be from this bond to this bond. Hydrogen atom will not go. Instead, 5 electrons are moved to hydrogen atom. The second one is 1 arrow is missing. Actually, there should be another arrow here. Then only this flow is completed, right? Third one, you can see, as I have explained earlier, this sulfur atom is hypervalent now. 1, 2, 3, 4, 5 bonds are there, right? So bond breaking should give to by a bond breaking and leaving of a group must take place. So I have corrected them like this. You can see one electron movement starts from here like this, and you get this stable Br minus. And as I have explained, now ignore the extra electrons here. The electrons on oxygen moves to hydrogen, and then in the middle there should be another full arrow, right? So this shows as a half arrow. It's not an half arrow. This is a full two-sided arrow, right? And then like this. And as I said, bond breaking takes place to give the valency as 4, right? Okay. So with that, let's see what we have to study in this course material. Now we are going to study about nucleophilic substitution reactions. Under that, we study SN2 reactions, SN1 reactions, and neighboring group participation, and the strength of the effects on those reactions, the strength of the nucleophile, the substrate effects, and solvent effects. Solvents, whether the polar protic solvents and polar aprotic solvents are going to behave differently. And then we'll study about elimination reaction. The main two types of elimination reactions are E2 and E1. And then we'll study effects of solvent polarity and temperature effects on elimination reactions. And then we are going to choose what type of reaction pathway a reaction is going to take, right? Whether it is SN1 or SN2 or E1 or E2. So for that, we have to consider the substrate, the type of the substrate, and the type of the nucleophile, whether it is nucleophilic or basic, whether it is a strong nucleophile or a weak nucleophile. Same way, same for the substitution reaction. And then finally, we study electrophilic addition reactions, and under that, we learn about carbon addition to carbon-carbon multiple bonds. Okay, so as now you know, first thing we are going to learn about is nucleophilic substitution reaction. So as the name implies, substitution is removing one group and getting another new thing added to the same molecule, right? So look at this reaction. You can have alkyl bromide, actually a bromide with 3 different groups attached to the carbon atom to which the bromine is attached. And what is happening here is bromine is replaced by OH minus. So finally, you get a compound with OH, and it's a substitution. One group is removed by another one, which we call a substitution, right? So what is happening here? You can see now the way I have written here is the molecule is inverse now. Now I have shown it pictorially shown what is happening here. Inversion of the configuration is happening here. Now you have learned your stereochemistry, and you know what will happen when the configuration is inverse, right? If the original molecule is R here, after the reaction, it will become S if something like this happens, right? So inversion of configuration has taken place in this SN2 reactions, right? So if you go look at the mechanism of this reaction, the pathway it is taken, it can be indicated like this. Electrons on the oxygen atom of OH minus that is the electron rich place here, the nucleophile, we call it a nucleophile, that because that species loves a nucleus, right? Because it is electron rich. So it is getting attached to a nucleus. So this carbon is the nucleus, which this nucleophile is going to attack, right? So free electrons on oxygen will get attached to this carbon, and this bond will be easily broken by taking 2 electrons onto bromine. It will be removed. But in between, when this doesn't happen immediately, the bond breaking and forming will take place at the same time. So with this the broken lines, I have indicated this bond is partially formed. Carbon OH bond is partially formed, and carbon Br bond is partially broken, right? So you get an intermediate stage where bond breaking and bond forming is partially taking place, and bond breaking is partially taking place. And after that, you get the product like this, right? So hope it is very clear to you now what is happening. The existing bond is broken and a new bond is formed, and you can see the OH is approaching from this side, and the leaving group leaves from this side, and the new bond is formed like this from the opposite side where the bromine was attached to the molecule. Okay, so okay. Now SN2, you know by now, you know what these letters denote. S is for substitution, N is for nucleophilic, 2 is bimolecular. So SN2 means nucleophilic bimolecular substitution. Why it is called bimolecular? Right? Now you can see here, if you write this according to the rate law, we can write the equation for the reaction, and in that equation we can see that rate is dependent on both molecules. Now this K is the rate constant. If you write an equation for the rate of the reaction, you know, for your what is it called, equilibrium reaction, for equilibrium reactions, you can write the rate of the reaction can be indicated using these expressions. So in this equation, for this particular SN2 reaction, you can see the rate is dependent on the concentration of both the substrate and the nucleophile. The substrate or the reagent. Reagent is a nucleophile. So the rate of the reaction depends on the concentration of both reaction. So it is called bimolecular. So you know what this S indicate, N indicates, and Y2 is there. Bimolecular nucleophilic substitution. Right. So we can draw an energy diagram for this reaction like this. Right. So according to the equation, you have the reactants and the product, and in between you have a transition state. We don't actually call this an intermediate. This is not actually existing, right? Then, or if it is, we can't isolate. Existing means it has to be a isolable species, but this is not a species which can be isolated. So it is not actually an intermediate, but a transition state, right? So, you know, now it is very clear to you. You have the nucleophile and the substrate. Substrate is the alkyl halide, and the products are the alcohol. According to our previous equation, the alcohol, Nu is depicting the nucleophile, and the leaving group is this. L is for the leaving group, right? So you can say only one hump is there, right? And from here to here, it is the activation energy of the activation energy indicated by delta G. This hashtag mark is for the transition state, right? And the transition state look like this: partially bonding, forming bond, and partially broken bond, right? And you have to indicate the small minus charge is there and a small negative charge is there on the leaving group as well, right? So hope it is clear to you. And this is delta G0 indicates the overall free energy change, right? When the reaction is taking place, the energy, the overall energy change or delta G0 is indicated from this difference. So stability of transition state. Now you saw what type of a transition state is there for SN2's reactions. So I have put in my print. Here I have indicated the substituent groups as R1, R2, and R3, right? So if you take all three, if all alkyl groups are replaced by hydrogens, it is going to be a methyl carbon here, right? And if one hydrogen is replaced by methyl, it is an ethyl group. And this is same way isopropyl and tertiary butyl. So if you take all these four types at the transition state, energy, the transition, the activation energy increases from left to right. When you go from this end to this end, you can see activation energy increases. and stability increases for towards this side, stability of the transition state decreases because these two groups are huge or large groups, bulky group, right? So when you okay, again an exercise there. Now it is something to deal with the stability of the transition state. Now see, consider the three bromides A, B, and C. A, B, and C are there. Giving reasons, select the correct energy diagram corresponding to their SN2 reaction. So you consider the SN2 reactions of all three, A, B, and C, and match the correct, match it with the correct energy diagram. You have 2 minutes, 1 minute. Okay, I think it's easy. You just have to consider the transition state and the activation energy involved in this. So you can see, you hope you have done like this, matching done by like this. This primary alkyl halide B has the lowest activation energy for its transition state because it has only one substituent, right? And the other one methyl group and the other two are hydrogen. So the next one is the next one is giving a energy diagram like this because it has two methyl groups and one hydrogen. In the transition state, you have two methyls and a hydrogen, and the next highest activation energy can be expected for this. And look at this one. Still, it is both these are secondary alkyl halides, but the difference here is this has a bulkier group than here, right? So it's according to what we have already studied now, it is going to have the highest activation energy, right? So look at my explanation in SN2 mechanism. So if a question is, you might not get the same question, but if you have to write an explanation for this type of a question, you should include this in the, not the exact thing, you should have the information like this. In SN2 mechanism, the nucleophile attacks from the opposite side of the leaving group. You know now. When the substituent groups are bulkier or more crowding, bulkier means large groups, access for the attack is difficult. You know, it is blocked line. Therefore, the reaction proceeds via a more unstable transition state. So, more unstable means it has to have more activation energy. So hope it is clear now. Okay. Okay. Write the structure of the product of SN2 reaction given below. You have a compound. Now what is this? If nothing, the group is not mentioned, it is a methyl group. This is not hydrogen actually. Just a line indicates it's a methyl group. Or otherwise, if it is chlorine, bromine, or iodine, or nitrate, or whatever it is, other groups have to be indicated, right? You have to write it. And without a group mentioned here, it indicates that it's a methyl group, right? So not hydrogen, remember that. So you have a bromine, all the other places, even though they are not indicated, hydrogens are there. And according to the valency here, carbon has a valency of 4. The other group which is not mentioned here is hydrogen, right? So by default, this is a methyl group, and all these carbon atoms are having 2 hydrogens each. And here bromine atom and a hydrogen. So it's undergoing a SN2 reaction, and the nucleophile is a CH minus cyanide group, right? So you have to write the structure of the product, right? So in SN2, what is happening is substitution. So the leaving group is bromide. So CN minus attacks this carbon. So write the structure of the product. Now, with the knowledge you are having now, I have been explaining what is happening in the SN2 reaction. Write the structure of the product. Now you know the stereochemistry. You have learned your stereochemistry, and at day school 1, we have discussed about the stereochemistry. You know what is indicated by this dotted, this broken wedge line and a solid wedge line. Write the stereochemical structure of the product. Okay, let's see. Check whether you have drawn a structure like this. Now you know in an XN2 reaction, inversion of configuration is taking place. So if the leaving group is attached like this, now this means away from you, right? This broken wedge line is to indicate the bromide group is away from the paper, right? So inversion of configuration takes place in this SN2 reaction, and now the CN group is attached towards you. It is projected towards you. So it's easy. We just have to remember in an SN2 reaction, inversion of configuration is taking place. So, yeah. Okay, I have mentioned it here. Sorry. So, as I have shown at my summary at the very beginning, we have to study about the solvent effects on SN2 reactions. Okay, SN2 reactions, right? Now you know the shape of the energy diagram for SN2 reaction. It's just products, the reactants here and the products here. One single curve like this, and on top you have the transition state, right? So what will happen if the solvents are different? Now, as I said, there are 2 types of solvents we are talking about here: polar protic solvents and polar protic solvents and polar aprotic solvents, right? Now here actually I have mentioned about the polar protic solvents. We are talking about the polar protic solvents, the effect of polar protic solvents. Now, if a polar aprotic solvent, what is polar protic solvent? You have to know what a protic solvent was. Those are the solvents which can form hydrogen bonds with other species. So if the nucleophile, this Nu minus is the nucleophile, is stabilized by hydrogen bonding, the nucleophile is stabilized by hydrogen bonding when a protic solvent is there, right? A solvent which can form hydrogen bonds. What are polar solvents? Polar solvents are defined as the solvents with high dielectric constant. They can solvate the ions. Now, if you have nucleophile is Nu minus, negatively charged ion. They can solvate the ion. Therefore, the interaction between ions are minimal. They can cover the ions. Solvate means cover the ions. So the interaction between the ions are minimal, right? So if you have a polar protic solvent, they strongly solvate the nucleophile. So nucleophile is stabilized. So therefore, the activation energy is high because it can't react, right? Yeah, it is going to be, the nucleophile is stabilized and it need more energy. The rate of SN2 becomes slower. You can understand when the nucleophile is stabilized, it is not, reaction to take place is difficult. Polar protic solvents are unfavorable for SN2. So compare the two diagrams here. Now this is for the reactants, same reactants in polar aprotic solvent. So the energy difference, the overall energy or activation, we consider the activation energy for the transition state. Now it is here. But what happens in what happens the same reactants and the substrate here in a polar protic solvent? So the nucleophile is going to stabilize the solvent is going to stabilize the nucleophile ions, right? And they are more stable and they are at a very lower energy state than when they are in a polar aprotic solvent. So that now the activation energy difference is this one. So you can see this energy is higher than the previous one because the nucleophiles are solvated and extra stabilized, right? So for SN2 reactions, polar protic solvents are unfavorable. Remember that. So polar aprotic solvents are favorable for SN2 reactions. So you read your course material and you can clearly understand that. And the easiest way to remember is this graph. Yeah, what happens? Why the reason for favorability or unfavorability is given here. Right. We'll move on. Right. Now, this is the same reaction. The alkyl halide, an alkyl halide. Okay. Now we are going to move on to the SN1 mechanism. You have learned about SN2 mechanism where bond breaking and bond forming takes place simultaneously. But in SN1 mechanisms, that doesn't happen. So it goes through a pathway like this. Look at this pathway. First, the bond breaking takes place. Initially, the bond breaking takes place, right? And then you will get a species like this. A carbocation is formed, right? Intermediate carbocation is formed. And then only the nucleophile is going to attack the C+ position, the carbon deficient place, right? And this reaction, breaking bond is slow, right? And it is the rate determining step. So step is going to be the rate determining step. And once the carbocation is formed, it quickly, the nucleophile get attacked. Nucleophile is attacking the carbonium ion, and it is a fast reaction. And step by step, if you write the mechanism, what is happening is now OH2 gets attached to this one, and since this oxygen is positively charged, this bond donates electrons, and hydrogen is removed as a hydrogen minus, hydrogen plus, right? So the final product is this, right? So you can see step by step, carbon-chlorine bond breaks, and then a carbocation is formed. This is the carbocation. Then this carbocation is attacked by the nucleophile, and then a proton dissociates. Since this is an unstable situation, proton has to leave, giving rise to a group like this, OH, right? So hope it is clear. Now look at, we'll see what type of energy diagram it will be for SN1 reactions. Earlier for SN2, you saw one hump here. Now in this, you have several, right? Ups and downs, right? Now see, first step, as I show, what happens is bond breaking and the formation of a carbocation, right? So is the reactants are here. It goes through a pathway like this, and this is the carbocation. But to form the carbocation, it has to undergo a transition state like this. Same way, the bond is partially breaking, right? So that is the first transition state, and we indicate it as TS1 or transition state 1. And then you get the carbocation, right? Like this. And we can indicate the activation energy as delta G transition state, right? And then you get another transition state where the new bond is partially formed, right? Like this. And it goes through a stage like this, or else sometimes you can ignore this small thing, or if you give it in more detail, you have a intermediate like this, and then it will turn into the products by removing OH, removing one H plus, right? So you can identify the corresponding reaction for each step. So for step 1, it is this up to here, it is the first reaction, and up to here, it is the second one, and finally, this reaction correspond to this step, right? So see the difference clearly, the two energy diagrams for SN1 and SN2, right? SN2 is bimolecular, SN1 is unimolecular, because for the rate determining step, it involves only the concentration of this alkyl halide, not the concentration of this nucleophile. We can see it in the next slide. Overall reaction is this. Alkyl halide converting into an alcohol, right? And the rate determining step is this one. The rest of the reactions are fast. So for the according to the rate law, rate is equal to the rate constant into the concentration of the substrate, concentration of this one. So the rate of reaction depends only on the concentration of the substrate, and so that it is called unimolecular. 1, SN1, unimolecular nucleophilic substitution. Okay. And stereochemistry of SN1. Now, you know the stereochemistry, we were learning about stereochemistry at our first day school. And when you consider the stereochemical aspects of the reaction, now we are talking about this, earlier we learned about the stereochemistry of molecules, right? Now here we are going a step ahead further, and we are going to talk about the stereochemical changes in a reaction, right? Now, the stereochemistry is this alkyl halide, this particular alkyl halide, where you have a phenyl group, methyl group, and a hydrogen attached to the carbon, to which the chlorine leaving group is attached, right? So the first step taking place in SN1 is the carbocation formation. This is the carbocation form. So the second step is the attack by the nucleophile, right? So this water molecule is going to act as the nucleophile. So when you have a intermediate like this, water nucleophile can attack from both sides, right? Look at the stereochemistry of this one. It can attack to this MTP orbital from this side or this side, right? But here you have a temporary stage where the leaving group is around the carbocation. Earlier it had been here, and it is around this side. And but quickly it is getting in the solution. It can move, and water molecule can attack from this end too, right? So if only the attack is taken place from this side, you will get a product like this, right? And when this chlorine is removed, is sent away from the carbocation, this water molecules is free to attack the carbocation from this end. So this situation is called asymmetrically solvated ion pair. This is an ion and the carbocation. Ion pair is cation and the anion. And this is called symmetrically solvated carbocation, because chloride minus is gone away, right? So when this happens, either from this end or this end, the attack can take take place, giving rise to this product or this product, right? Now in SN1, you saw only inversion from the group which is leaving, from the end where the group is leaving, no attack is taking place. But here, since the carbocation is formed, the nucleophile can attack from both sides, giving rise to both type of products, inverted product and the product where the stereochemistry is written. And we called it 100% racemization. So if this is the S product, this is going to be the R product. This is not so. I don't know what the stereochemistry of the products here. I haven't checked, but you can get R product and S product as well, a mixture of these, and we call it racemization. But compare it with the SN2 situation where only inversion is taking place, right? So if the original compound is R, in SN1 you got the S product, but here R and S both, right? So hope you could get it clearly. Okay, so same way we learned the factors affecting SN2. Same way we can consider the factors affecting SN1 as well. So first factor we are considering here is ease of removing the leaving group. So you saw from the alkyl halide, the halide is leaving. So if the halide is tightly bonded, less tightly bonded. Remember, it is if the halide is loosely bonded, less tightly bonded, it is easier to break the bond. So if you have a series like this, you know, fluorine, chlorine, bromine, and iodine. The series, it goes down like this, right? The CF bond is the strongest and difficult to break, right? The bond strength increases from this end to the strongest bond is the CF bond. Right, please switch, turn off your mics, right? Okay, so the weakest bond is carbon iodine. Iodine is a large atom and the bond strength is lesser when you compare with chlorine, and bromine, right? So it is easier to break. And stability of the carbocation. The more substituted the carbon atom, more stable it is and easier to form. So when you compare it with this methyl cation, carbocation, ethyl, this primary one, secondary and tertiary, more stable carbocation is this tertiary carbocation. So according to the more substituted, it is easier, it is more stable and it is easier to form. That you know, this part you already know, right? So consider those things also when you are writing SN1 reaction mechanisms, right? So adjacent alkyl groups increase the stability of the carbon, that you know, right? So here are two energy diagrams to show you the solvent effects on SN1. So earlier we consider the polar protic and polar aprotic for SN2. Now this is for SN1. So if you have the reaction taking place in a polar protic solvent, less polar protic solvent like this, for example ethanol, right? So you can draw a diagram like this. When you compare it, the same reaction happening in a more polar protic solvent. For example, water. When you compare ethanol and water, water is more polar than ethanol, right? So you will get a graph like this, plot like this, where the activation energy. It's strong here. Yeah, activation. This part is wrong. This E2 is wrong. It should be the arrow should be here. The distance should be here. The activation energy to form. I have made a mistake here in indicating the delta E2. The activation energy for this. Okay, right. It's right, correct, right? So actually we are talking about the activation energy for the transition state, right? So delta E1 for polar protic solvent. For example, ethanol is this much. delta E1, which is higher than delta E2. When you have a more polar protic solvent, transition energy is reduced, right? So why? Polar protic solvent, the reason for this one is the carbocation is stabilized here due to solvation, right? Carbocation stabilized in more polar protic solvents, right? Polar protic solvents stabilize the carbocation, so that if you do the same reaction in more polar solvent, the carbocation is more stabilized, and you can see the activation energy is lower when compared with the less polar reaction, right? So this activation energy is correct. What I have indicated is correct in both graphs, right? We are talking about activation energy for the transition states, right? And here the alkyl halide is also more stabilized in more polar solvent, right? Compare the energy of the ground states also in two situations, right? Okay, so this is another aspect we are talking about in SN1, that is rearrangements in SN1, right? So if you have a alkyl halide like this, now I'm here summarizing what you have to read in the book, right? So this is one aspect, the rearrangements, where you have two bulky groups attached to the carbon atom to which the Levy group is attached, right? So here you can see a very huge group is attached to this carbon atom, and the other one is CH3 and a hydrogen, right? So in a case like this, now this is how the carbocation is formed. Leaving of the chloride ion will give rise to a carbocation formation here, C+ here. But if you have if you have groups like this, there are certain tendency that 1-2 shift of hydrogen atoms taking place. That means shift of hydrogen is hydrogen can move into this place, giving rise to a more stable carbocation. Right? You can see here it is a secondary carbocation. Only two alkyl groups are attached to this carbon atom. But if this hydrogen is shifted to this carbon atom, you get something like this. Here, then the plus charge will be on this carbon atom, and which now it is a tertiary carbocation. You have this group, 3 R groups attached. So if you get a secondary carbocation form in a compound like this, definitely this hydrogen shift will take place, giving rise to a more stable carbocation. So the attack by the nucleophile take place on this carbon atom, not this. This is also happen. This also might happen, giving rise to a mixture, right? So I have in this reaction, I have indicated only the product formation when it is attacked by this tertiary carbocation, but small number of molecules will be in the secondary carbocation stage, and the product of this also can form, right? And a major product will be the substitution on this tertiary carbocation. So you can see it like this, OMe, methanol. This is the, we have written the reaction for the reaction with methanol. So it takes place like this, attack on this one, and hydrogen will remove, giving rise to OMe added to as the final. Instead of OH, we were talking about OH addition in previous cases, but in this particular example, it is methanol which is acting as the nucleophile, right? So hope you understand what is happening in rearrangements in SN1 reaction. So basically what you should understand is in SN1 reactions, rearrangements can take place where the reaction can go through a more stable tertiary or secondary carbon. If it is a primary carbocation which is formed, it will definitely, if the other facet, other environment, the rest of the part of the molecule is favorable for a hydrogen shift, it will definitely take place, giving rise to a secondary carbocation if it is a primary. So since in this particular example, it is the secondary carbocation which can easily give rise to a tertiary carbocation. So that will happen. And finally, you will get a mixture of, this is going to be the major product. product out of the tertiary carbocation, and small percentage will be the product of the secondary carbocation. Right. So when you compare SN1 reaction, now we have finished talking about SN1 and SN2. When you make a comparison on both, you can see the mechanism in SN1, 2-step. Here it is 1-step. And the graph also with several humps in this SN1, and in SN2 only one curve. And kinetics, this is first order, this is second order. And reagent nucleophilicity is unimportant to the rate here, and this is rate controlling because both concentrations matter here since it is bimolecule. And the substrate more favorable is tertiary, and it goes like this in SN2. And solvent effects favored by the solvent, the polar for SN1 reaction favored by polar solvents, and protic solvent inhibit the nucleophile. And stereochemistry, here it is partial racemization with inversion, both takes place, and here it is inversion only. And the reaction conditions, usually acidic or neutral, and this is usually basic or neutral, right? So when you go through the book in detail, read the things in detail, you will find all these things and understand properly. Okay, so to test what you have, whether you have learned everything, got grasped everything what I have explained right now, let's do this exercise. Ethyl chloride undergo hydrolysis in the presence of sodium hydroxide. Strong base, sodium hydroxide is a strong base, and out of it you can get OH, right? So OH minus. The rate of this reaction is increased when sodium hydroxide concentration is increased. Maybe somebody has practically done this reaction and found out that reaction is going to increase when sodium hydroxide concentration is increased. Explain the above observation, giving mechanism of the reaction. Draw the energy profile for the course of this reaction. So try to understand the question and find out the answers. Actually, give a try. I will give you 5 minutes. 15. Okay, let's see now. To save time, I will now, now you can see the substrate is ethyl chloride and the the reagent is sodium hydroxide. So out of sodium hydroxide, the nucleophile rising is OH minus. And the rate of reaction is said to be increased when the sodium hydroxide concentration is increased, right? So we can now, if the reagent concentration is also involved in the rate determining, it's definitely, we can say it is a bimolecular reaction. So see my answer. When you are writing answers, you have to include all these in your answer. Rate of this, not this, the rate of this reaction is determined by the concentrations of both reactants. It's already mentioned there that OH minus concentration matters, so that the rate is equal to the constant and both concentrations. You have to multiply the rate of both concentrations of both. So therefore, the reaction proceeds via SN2 mechanism, bimolecular. According to this rate equation, it's bimolecular. So a bimolecular reaction will take place like this. Now you know the pattern. Now it attacks from this side. This is the substrate. It's a primary alkyl halide, and the nucleophile is anionic, and it is a strong nucleophile. Now read your book and understand what are strong nucleophiles and what are weak nucleophiles. I'm not going to explain all this here. Read your course material and find out the two different types of nucleophiles, strong and weak. And also it is anionic. And this is how the transition state is indicated: partially bond formation and partial bond breaking, like this, giving rise to a 100% inverted product, right? So this is how the reaction is taking place. So now the information you can get from the description here is sodium hydroxide concentration is involved the rate determination. So that it is definitely going to be SN2, right? So that's all you have to write. Second, draw the energy profile that you can write. Energy profile for SN2 reaction. You know how to draw it, where to indicate the reactants, the intermediate, the transition state is this one, and the product are this, and single curve like this, right? So the second exercise, consider the solvolysis reaction of 2-bromo to methyl propane. So when you get the IUPAC name, you should be able to draw the structure of the compound, right? You know that now, by now. In ethanol, the reaction solvolysis of this compound is taking place in ethanol. Give the mechanism of this reaction. Compare the reaction rates of this solvolysis reaction if this reaction is carried out in ethanol in water. Now, initially it is said that it is taking place in ethanol. So you have to compare the rates if the same reaction is taking place in not in ethanol, but in ethanol and water. Instead of ethanol, you have a solution of ethanolic water solution. Give reasons for your answer. Draw energy profiles for both reactions showing the effect of solvents. Okay, same thing we have discussed in the previous 2 slides ago. I was discussing this. So just try to give the mechanism and compare the rate. Find out in which solvent the rate is going to be faster. In other words, in which reaction the activation energy is less. And give reasons. Draw the energy profile. Compare. You have to draw. When you are asked to draw the energy profiles, you can't draw one after the other, one below the other. When you are been asked to compare the energy profiles, you have to draw it side by side, showing the energy differences. Otherwise, it is difficult to compare the energy levels, right? So you draw 2 profiles side by side. Okay, this is actually one of the final exam paper questions. To save time, let's move on. You have to write something like this. Your answer should include these things. So the mechanism for the reaction in ethanol would be something like this. Similar reactions are given in your book, right? So you have to write something like this. The carbocation formation, and ethanol is a weak nucleophile. Neutral molecule, not an anion, weak nucleophile, and it will go through carbocation formation. Reaction goes through carbocation formation like this. So this is the reaction you are going to write, and the answer should include. This is a two-step reaction. You can see it is actually it is going to be the rate determining step is this one. So SN1 reaction. So rate determining step involves substrate concentration only. A stable carbocation intermediate is formed. So polar protic solvent solvate the carbocation. I told you this carbocation is solvated by the polar protic solvent. This is a polar protic solvent. So it covers around this and the carbocation is stabilized. So nucleophile can attack from either side of the carbocation. So from each side it can attack, right? Like this. And it goes through this intermediate stage and hydrogen is left like this. Another ethanol molecule can abstract H+. And the final product is this. So since it is attacking from both sides, partial racemization. This lead to partial racemization because this one gives the R products from this end, ROS, or the opposite, if it is attacked from the other side, the opposite stereochemistry. So rate of the reaction for the second part of the question, rate of reaction is higher in aqueous ethanol than in ethanol. Water is more polar than ethanol. That is the reason, right? So this, yeah, what is this second one? Yeah, rate about the rate. The reason for that, water is more polar solvent than ethanol. Water solvates the carbocation more strongly than ethanol does. Therefore, the carbocation is more stabilized in water than in ethanol. Hence, the energy of activation is less in water than in ethanol. Therefore, when the reaction is done in increasing amount of water, the rate is increased. Water is more polar than ethanol. That you have to know, right? So when you are reading the book, you will come across several examples related to this explanation, right? So these are the two types of energy diagrams you have to draw. And when you are drawing, someone should be able to compare the energies. So the activation energies. Here it is higher in ethanol, less polar protic solvent, and this is more polar with less activation energy, right? So we'll move on. And we'll talk about elimination reactions. As I told you, there are two types of eliminations we are talking about. E2, bimolecular, same way as SN1 and SN2. E2 means bimolecular elimination. E1 is unimolecular elimination, right? So in bimolecular elimination, same way, bond breaking and formation takes place simultaneously, right? And here a carbocation is formed. The reaction in unimolecular one, it goes through a carbocation formation, right? So we'll look at this E2 in detail. You can see removal of proton by the base, right? This B minus is the base. So elimination takes place when hydrogen is abstracted by a base. So this is acidic hydrogen and it is abstracted by a base, right? And the elimination of the leaving group. X is the leaving group, maybe most preferably bromide, iodide, or something halide group, right? Or something else even, right? So intermediate stage is transition state is this one in E2, and the rate determining step is both concentrations of both, right? Like same way as same thing as SN2, right? So this is the transition state. Finally, elimination is parts of the molecule is removed. While some atoms or groups are removed, so that it will give rise to a alkene or electron deficient compound like this. Removal of groups or atoms. And whereas in E1, elimination of the leaving groups takes place first. And this is the slow reaction, giving rise to a carbocation. You can see the carbocation. And then the base attacks. Base abstract the acidic hydrogen, and the electron transfer will take place like this, giving rise to a pi bond formation like this, right? So this is the basic thing happening in E2 and E1. So depending on the leaving group and the base attacking, you can substitute those for the base and leaving group and write the mechanisms easily. So the general reaction, what is taking place in E1 and E2 are these, right? So same way we can compare the energies for E1 and E2 like this. In E2, bimolecular, both concentrations matters, base and the substrate, and goes through one transition state, giving rise to products. And it's like this. The shape of the curve is like this, right? So the reaction, the other one goes through carbocation stage. Products are, the reactants are here, products are here, one intermediate, which is a carbocation, and it has two transition states, same way. Okay, so same way we can compare the E1 and E2, and when you study the two types of reactions in detail, you will see that mechanism is two-step here in E1, and this is one step. Reaction kinetics, this is first order and second order. And nucleophile, this is important. Nucleophile in E1 is neutral and weak acidic, and here it is anionic and strong basic. Substrate, the ease of elimination is towards this way, tertiary to secondary to primary, and it is the other way in E2, and this is favored by low polar solvent. E2 is favored by low polar solvent. Stereochemistry, not selective. Here you have to get a trans arrangement for the elimination. Now in this elimination, I have not indicated the stereochemistry of the substrates and the product, but when you study it in detail, you will see the trans arrangement is required for E2 elimination. This is, it doesn't matter, any arrangement is okay for E1 because it is unimolecular. And reaction conditions, usually acidic or neutral. This has to be basic or neutral, right? So if you have, now when you are doing a reaction, maybe an alkyl halide reacting with the base, right? We don't know what type of a reaction is taking place, right? So to compare, to find out what type of a reaction is taking place, you have to, you can just consider the type of nucleophile, the substrate, and the solvent you are using for the reaction. So first you check the nucleophile, right? If the nucleophile is a neutral or a weak nucleophile, then most probably the reaction that is taking place is going to be SN1 or E1. Neutral and a weak nucleophile, maybe water, methanol, ethanol, or maybe a weak neutral molecule or a weak nucleophile. Not, it is not going to be SN2 or E2 if the nucleophile is neutral and weak. If it is anionic, if it is neutral, if it is anionic, then it can be SN2 or E2, right? So remember, it is neutral and weak, SN1 or E1. If it is anionic, SN2 or E2. And then next, check the substrate.
Madam,
Yes.
please say it again. If it is neutral and
if the nucleophile, now first we are checking the nucleophilicity of the nucleophile. If the nucleophile is a neutral or a weak one, like water, methanol, ethanol, then the reaction will go through SN1 pathway or E1 pathway, right? So you compare the reaction we have studied earlier. If the nucleophile is an anion, like OH minus, then it will take place through SN2O E2, right? Now, when a reaction is taking place in a glass jar, these two types of reactions fight each other because we can't instruct them to take place in SN2O E2 mechanism, right? The reaction will take place considering the other environment in the reaction mixture. So if the nucleophile is anionic, most probably SN2 and E2 reactions fight each other, right? And then to find out whether it is actually SN2O E2, you have to consider the other factors as well. Sometimes when you do a reaction, both products, SN2 and E2 products will be formed. When you look at the products of reactions, now we are not going to give you reactions like that because it is complicated. But in a reaction mixture, these two types can take place. Maybe SN2 is more prominent and E2 is less prominent, and the products of E2 are very little. And the major reaction which is undergoing is SN2. Now, when you are checking the nucleophile to predict, to find out whether it is SN1, SN2 or E2, we can predict. If the nucleophile file is anionic, then SN1, SN2 or E2 can take place. And then you check whether the substrate is primary. This can take place if the nucleophile is anionic, right? Say primary alkyl had sodium hydroxide. So it is sodium hydroxide that gives the anionic nucleophile. You check the substrate, whether it is a primary alkyl halide or a secondary alkyl halide or a tertiary. If it is primary, it is not going to be E2. It is going to be SN2 only, right? Understood? If it is a tertiary substrate, only E2 reaction will take place. So for a tertiary, so when it comes to here, the nucleophile should be an anion, and the substrate should be a tertiary one, and it is going to be E2 mechanism, right? So for E2 also, I told you earlier, it has to have a trans arrangement. The leaving group and the hydrogen, which is getting abstracted, has to have a trans arrangement. So if it is the tertiary substrate, it is difficult to predict whether it is SN2 or E2, right? Then you have to check the solvent. If the solvent, no, so you are coming down from this place. Nucleophile, consider the nucleophile and then the substrate. And if you have a choice between SN2 and E2, you have to check the solvent. If it is polar and protic, E2, and polar and aprotic, it is going to be SN2. If the substrate is secondary. If it is primary, we can definitely say it is SN2. If it is tertiary, we can say it is E2 only. But when it is in the middle, secondary, these two can be there, then we have to consider the solvent. So when you read the book, you have to read the book carefully, and then you have to, I have given a key like this for you to understand easily. It is not given in the book, but this is the way you have to think. I have made the things easier for you, right? Okay, so you read the book and try to understand, because with this one only, with this, by going through the contents in this slide, you can't understand everything, right? So this is
Madam,
just
මේකට කලින් මේ slide එක පොඩ්ඩක් දාන්න පුළුවන්ද?
okay. This one.
ඊට කලින් එකක්. ඔව්, ඒක ඊට කලින් එකක් madam.
Maker.
ඔව්.
Okay, so
ඊටත්
just
කලින් එක madam.
this answer මේක ඔයගොල්ලෝ පොත්වලින් බලා ගන්න. පොතල අපිට
හරි
දැන්
madam.
10ට මේක මම හිතන්නේ තව level 4 එකක්ම තියෙනවා, කවුරු ඉන්නවද දන්නේ නැහැ next එකට යන්න. Okay.
Thank you madam.
So it's here again, I have a question here just to explain the these arrangements, giving the mechanism. This is again a final exam paper question. Giving mechanisms, predict the products when the following two compounds A and B are reacted with sodium methoxide. This is NaOH, sodium methoxide in ethanol. It's a strong, it's a base, right? In ethanol. Comment on the relative rates of the reactions. Now, similar example is there in the book. You think how to, I will give you a few minutes to think what is happening here and the type of reaction taking place, and explain why the rates are different. Okay, now let's see how you are going to explain it, write the answer for this. Now, when you look at the two structures of A and B, you can see the only difference is here, the stereochemistry of this carbon atom, right? So your answer should be something related to the, this question is based on something related to the stereochemistry of this position. Just by glancing through the structures, you can predict it. Let's see how you are going to construct. Now, in this nucleophile, now it is said sodium ethoxide in ethanol, right? So the nucleophile is going to be an anionic one. NaOET is the anionic coming out of NaOET is OET, right? So it's a strong basic nucleophile. It's a base, strong base. Substrate is tertiary, right? So by going through my key, I have given earlier in my earlier slide, you can find out it is going to be a nucleophile which is an anionic and a strong base, and the substrate is a tertiary one. this cyclic substituted cyclic hexane. So both E2 and SN2 pathways are possible. SN2 is not favorable due to steric hindrance because there are 2 beta hydrogens available, right? So E2 is favored, right? So you can see when I draw the structures for this one, these are the 2 compounds. When you draw, it is going to be, if it is E2, this is this one, how it is going to E2 mechanism, this compound, and this one is like this, right? So this is, when you look at this one, it gives a stable conformation like this. This is the chair conformation you can draw for this one. And when you make these methyls, actually we are considering about the stereochemistry of this, the hydrogen attached to this carbon atom. In E2, the elimination takes place like this. And you have to have a trans arrangement like this. Here it is a trans arrangement for E2. Right? In this one, you don't have any arrangement because it is equatorial. Right? So, as I explained in my first day school, these chair conformations can flip to give you the other chair conformation like this. So, when they flip, the equatorial groups will become axial, and axial groups will become equatorial due to flipping. So the stable conformation is of this compound A is this, and elimination elimination will give rise to a product like this. Now in this mechanism, stable conform itself has the stable conformation. No, the stable conformation of this compound is this one, right? Where the trans arrangement is not there. When you draw, the stable conformation is this, because here this one is stable because when you get this chair structure due to 1,3 diaxial here with this hydrogen, it has diaxial interaction. This chair conformation is not stable. So in this case, when they are axial, equatorial, no diaxial interactions. So this chair is the stable conformation. But in this case, in the compound B, this is the stable conformation, where the diaxial, 1,3 diaxial interactions are not there. But it doesn't have the trans arrangement for elimination. See, other conformation only has the trans arrangement of hydrogen and chlorine, which is not, this is not the stable conformation because it has diaxial. Now with this hydrogen, it has, with this hydrogen, actually it has diaxial interactions, right? But anyway, if you have the less stable conformation, it will undergo elimination like this to give you this product. So let's go to the anti-periplanar. Anti-periplanar, and we call it trans or anti-periplanar arrangement leading to anti-elimination. This is anti-elimination, anti or anti-elimination, or trans elimination, right? So when you are writing the answer, you have to explain it step by step. In the stable conformation of A, 1 hydrogen atom and chlorine are in the anti-periplanar arrangement. This is required for elimination. That was clear to you. But when you look at this one, stable conformation has the required stereochemistry, which is anti-periplanar or trans arrangement. This is required for E2. Since it is the most stable conformation and at any given time, its concentration is high. So hence it undergoes the reaction fast. But in B, the stereochemical requirement for E2 elimination exists in the less stable conformation that I have explained a little while ago. Since its concentration is low, the reaction undergoes slowly with B. The elimination reaction with B is slow. Therefore, A undergoes reaction with NO2, E2H relatively faster than B. Hope you have got it clearly. For that, when you consider actually, you have to consider the reaction, and you know SN2 is not favorable due to ferric, because for SN2 to this position, SN2 will take place by attack on this place, and which is difficult because of the ring structure and the other groups attack. So definitely E2 is taking place, and E2 is more favorable when you have when it is undergoing anti-elimination or anti-pen arrangement in the structure. In the structure when of the stable configuration. So this is how you have to give the answer. So I'm giving these model answers because when you are writing, you write everywhere and maybe your answer is there, but not in clear order. So if you understood the things, the facts properly, you have to construct your answer step by step. You can give the explanation like this, right? So as a model, how to write clear answers I have given, right? So each detail, maybe not for each step, you don't have to write the same exact word, but the information what I'm trying to express here should be there when you are writing answers. Okay, so another one, giving reasons. All these questions are from past papers, right? So you can get the idea the type of questions you are getting at the final examination. Giving reasons, predict the mechanistic pathway and the products of the two following reactions, right? Same compound, difference is here the solvent is methanol, here the solvent is dimethyl sulfoxide here. A similar example is there in the book. So to save time, we have to stop at what is the time now? 9:54. We'll see. Now it is now look at the substrate. It's a secondary alkyl halide. You have one alkyl group here, another methyl group here. The same substrate, only difference is the nucleophile is also the same. Difference is in the solvent, right? So when you look at this one, secondary substrate, anionic nucleophile, strong base. So it can be SN2O, E2, right? Cannot be SN1O, E1. Anionic nucleophile. Right, for SN1, it has to be neutral nucleophile. Right, so for this one, the solvent is a polar protic solvent. If it is polar protic, definitely E2, right? So it goes like this. Anti-arrangement, anti-periplane arrangement or trans arrangement. The most substituted alkene is obtained, right? And in this case, this is a polar aprotic solvent. So with the aprotic solvent conditions, E2 cannot take place. With these aprotic solvents, with the aprotic solvent, SN2 is preferred. I have explained in one of my previous slides. Polar aprotic solvent definitely favor SN2 reaction. So SN2 reaction is like this, right? And here it is elimination. It is a substitution. SN2 is a substitution, and inversion of configuration takes place. So next thing, electrophilic. So we were talking another type of reactions is addition reaction. Earlier we discussed about elimination, and before that substitution, and this is addition reaction. So addition takes place into a electron deficient place on a molecule. So like this. Now this reaction we have studied for your level 3, addition of HBr onto alkenes, right? So you are somewhat familiar with the type of the reaction. So we don't want to discuss much about this. You have already written the mechanisms also. So carbocation, and the carbocation is attacked by the this nucleophile onto the electron deficient carbon, right? So taking place in 2 steps, and during these reactions, carbocation rearrangement also can take place. So it is as an evidence for carbocation formation. You can take this reaction where when the addition is taking place, 2 types of products are formed. This is going to be the major product, and this is the minor product. So a minor product is taking place due to a tertiary carbocation formation, right? So rearrangement is possible, and it gives rise to tertiary carbocation and this one. So the formation of two products like this is an evidence for the reaction to take place through a carbocation stage. Right? Okay, so if I summarize what we have learned today, or what you have to learn in your course material, I don't have to explain all this. Now we have discussed about alkyl halides that can undergo two kinds of nuclear SN2 and SN1 reactions, and eliminations are also two types, E1 and E2. SN2 and E2 are bimolecular, one step that you know, and we have this one unimolecular and two step. SN1 lead to a mixture of stereoisomers, racemization. SN2 inverse the configuration. That inversion of configuration takes place in SN2. I remember that umbrella thing. Inversion is that. The major product of elimination is the most stable alkene. Now that is called the Zaitsev rule. You have learned it at A levels and level 3 also as the Zaitsev rule, right? Now you know why it is happening. We were just learning that most stable product is forming, but you should be able to explain why it is so. SN2 and E2 are favored by strong nucleophile or strong bases. Bimolecular one, strong nucleophiles, this one bimolecular. Both nucleophile and the substrate are involved. If and SN2 is favored by primary alkyl halides. E2 reactions are favored by tertiary alkyl halides. Electrophilic addition on carbon-carbon multiple bonds takes place via the most stable carbocation and occurs as anti-addition. So that is what we have discussed in the previous slide. So with that, we will conclude our discussion. So you know, there's a great field to study. All these things we have discussed, I explained in detail in your course material. So you can go through the book several times to understand these things properly. And you know, we have the CAT1 test on January 1st, right? So if you have any questions, you can ask now, or else we can stop the day school, because I think there's another day school scheduled for level 4 at 10 o'clock, right? Okay, so shall I conclude the day school now? So hope everybody has put the entered your name and registration numbers in the chat box. If you haven't done so, please do so.
Excuse me, madam.
Yes.
Can you upload this presentation and the previous one to the LMS?
We were asked to put only one recording, or the give, if it is the recording, give the link. And if we are uploading the presentation, only the presentation. And if the recording quality of the recording is good, I will upload the